Epithermal mineral deposits. Epithermal mineral deposits are a subgroup of hydrothermal deposits that have specific formation criteria. Mineralization is associated with young felsic to intermediate magmatic centers and forms at shallow crustal depths. Epi means shallow and refers to deposits that formed less than 1,500 meters below the paleo surface. Globally, epithermal deposits are located in young igneous rocks associated with active or past subduction. This map shows the location of the different types of epithermal deposits around the world and clearly shows the association of most deposits with young, active, subducting plate margins. Most deposits are tertiary age or younger, less than 66 million years, as older deposits have been eroded in areas of active uplift. Epithermal mineralization, which postdates host rock formation, can be hosted in any rock type. However, they are typically hosted by intrusive or extrusive igneous rocks or volcaniclastic sedimentary rocks. This is primarily due to their formation environment in subduction-related arc and back arc environments. This image shows a cross-section through the Golden Cross low sulfidation gold-silver deposit in Coromandel, New Zealand, which is hosted by andesite and dacite. Epithermal deposits form in the top 1,500 meters of the crust at temperatures between 200 and 300 degrees Celsius from low salinity fluids that contain less than 3 equivalent weight percent NaCl. There are two types of epithermal deposits: low sulfidation systems, which form distal to the magmatic center, and high sulfidation deposits, which are more closely associated with acidic fluids and form closer to the magmatic center, commonly adjacent to porphyry copper deposits. Low sulfidation hydrothermal fluids are a combination of magmatic and meteoric water. Meteoric fluids, those formed from rainwater, percolate down through the crust and become heated due to the elevated geothermal gradient caused by the igneous intrusions. They mix with magmatic fluids that have exsolved from the cooling intrusions and rise back through cracks in the crust. Vein formation takes place primarily due to depressurization and phase separation from neutral pH fluids. Dissolved elements such as gold and silver can't remain in the vapor phase, and so the liquid phase becomes supersaturated, resulting in the precipitation of quartz veins with associated mineralization. This process is commonly referred to as boiling, although it is not boiling according to the generally accepted definition. Precipitation occurs episodically at around 200 to 300 degrees Celsius and results in open space-filled textures such as crustiform, coliform, cockade, or bladed veins, and gold-bearing breccias. In areas of active volcanism and geothermal activity, low sulfidation deposits are forming beneath hot springs. This is an image of Champagne Pool at Waitapu geothermal area in the Taupo volcanic zone of New Zealand. The TVZ is a back arc basin that lies behind the Tonga Kermadec subduction zone. It is associated with extensive active volcanism and hot spring activity, including Waitapu. Champagne Pool gets its name from the carbon dioxide exsolving from the water, and is considered to be a modern analog for ancient low-sulfidation epithermal deposits. The orange crust around the edge of the pool is actively precipitating from the hot water and is composed of orpiment, an arsenic sulfide, and stibnite, an antimony sulfide, and contains 60 grams per ton gold and 100 grams per ton silver. The grayish-white silica sinter returns assays of 8 grams per ton gold and 6 grams per ton silver. This sample shows the characteristic banded veins typical of epithermal deposits. The light-colored bands are composed of quartz and carbonate, either calcite or siderite, whereas the dark-colored bands contain extremely fine-grained sulfides such as pyrite, chalcopyrite, galena, or sphalerite within cryptocrystalline silica. The lower, darker subparallel bands are described as crustiform, whereas the semi-spherical, lighter-colored quartz carbonate bands are coliform. The dark sulfide-rich bands host the gold. This photo shows cockade, colliform, and bladed textures in a quartz, white and gray, and rhodochrosite, pink, epithermal vein. Epithermal vein textures are often extremely complex and represent multiple episodes of boiling and precipitation. The force of rapidly expanding hydrothermal fluids as they rise through the crust can fragment the host rock. Minerals precipitate out of solution as a result of rapid pressure drop and cement the clasts together. This image shows a gold-bearing breccia from the low-sulfidation Sleeper mine in Nevada, USA. Note the fragments of crustiform banded veins in the bottom right corner of the image. High sulfidation epithermal deposits form proximal to the underlying igneous intrusions, primarily from acidic magmatic fluids, with little contribution from meteoric fluids. Acidic fluids dissolve the country rock, leaving behind vuggy silica deposits with disseminated mineralization. Veins are not common in high sulfidation epithermal deposits. This photo was taken at Nansatsu in Japan, the type locality for high sulfidation epithermal gold deposits. High sulfidation epithermal deposits are also associated with surface geothermal features such as mud pools and fumaroles. This image shows a mud pool at the Reykjavík hot springs area in Iceland. Mud pools form when acidic gases dissolve overlying rocks to form clay. The clay mixes with rainwater to form thick bubbling pools. The acid sulfide fluids that form mud pools are instrumental in forming high sulfidation epithermal gold deposits. Ore textures in high sulfidation deposits differ significantly from their low sulfidation counterparts. The highly acidic magmatic fluids eat away at the country rock, leaving behind vuggy siliceous alteration zones, and gold, plus or minus copper, is commonly hosted in disseminated pyrite. The red rusty patches in this image, which is from the Nansatsu deposit in Kyushu, Japan, reflect the high sulfide content of this rock. There is considerable variation in grade and tonnage from epithermal deposits, but generally low sulfidation vein and breccia type deposits are small, high-grade deposits that are mined underground, whereas high sulfidation deposits, which comprise primarily disseminated mineralization, are significantly larger but much lower grade. Low sulfidation gold deposits are amongst the richest in the world and contribute significantly to global gold production. The world-class Hishikari gold mine in Kyushu, Japan has an average grade of 40 grams per ton gold and has produced 6.2 million ounces of gold from 3.9 million tons of ore. Much larger high sulfidation deposits are commonly associated with porphyry copper deposits in South America and Southeast Asia. Gold grades in these deposits are typically much lower, although deposits such as El Indio in Chile host grades up to 178 grams per ton gold. Copper is often a profitable byproduct in high sulfidation epithermal deposits. In summary, epithermal deposits are vein, breccia, or disseminated deposits that form at collisional plate boundaries. They are associated with young magmatic centers, typically of felsic to intermediate composition, and are primarily hosted in volcanic and volcaniclastic rocks. They form in the top 1.5 kilometers of the crust from mixtures of magmatic and meteoric fluids as a result of phase separation. Low sulfidation epithermal deposits are characterized by neutral pH, low salinity fluids in a temperature range of 200 to 300 degrees Celsius and form high-grade, low-tonnage banded vein or breccia deposits. High sulfidation epithermal deposits form from acidic fluids and typically result in leached, low-grade, high-tonnage deposits. Geothermal features such as hot springs and mud pools are considered modern analogues to ancient low and high sulfidation mineralizing systems, respectively.